Very good morning to all. After 2 days off, I welcome you again on day 5, session 1. I request Professor Samath introduce our today's speaker, Mr. Jimit Mehta. Professor Samath.
Thank you, Professor Yagnesh. Hello, everyone. A very good morning to all of you present over here for attending Faculty Development Program on Automobile Engineering, Past, Present and Future, sponsored by AICT IST. Myself, Samar Shelat, faculty from Automobile Engineering Department of ADIT College, heartily welcome each one of you present here. Today, we have among us Mr. Jimit Mehta, Senior Quality Engineer from Tesla Incorporated, for delivering a technical session on challenges with mass production of EV battery pack. I am also happy to say that he is one of our prestigious students. Now he is our alumni. Thank you, Jimit, for accepted our invitation and ready to deliver a technical session. Now I would like to share a brief resume of our expert. He has done his diploma in automobile engineering from GTU in 2013 and bachelor degree in automobile engineering from ADIT College in the year of 2016. He has done his master's in mechanical engineering with specialization in manufacturing and design innovation from University of Texas at Dallas in the year of 2018. He has also done various major projects and participated in Baja competition, which was held in 2015-16. He worked as a quality engineer for Model 3Y HV battery manufacturing since 2019. And additionally, he has been prior to that worked with Tesla for 15 months across the general assembly and service team. Currently, he works as a senior quality engineer for new programs and factory launch since February 21. Now, not much wasting of time to start our technical session. I request to Mr. Jimmy Mehta to start the session. We will learn a lot from this technical session. Thank you.
Hey, thank you so much, sir. Thank you, Sanjay sir and Yagnesh sir as well for this opportunity. Let me start sharing my screen. I hope you guys can see my screen. Good morning to everyone once again. For today's presentation, I'm going to speak on the challenges with the mass production of the EV batteries. And before we go into the full technical details, just an overview for the presentation that I'm going to speak about today. It's going to start with a very brief introduction about myself, which I think Samad sir has already captured a pretty bit all of it, so would not be wasting much time on that. And then just to get the stage up and there, would be speaking a bit about what the electric vehicles trend has been over the last decade and what is an anticipated and the predicted market growth over this coming next years, which seems to be very much interesting for the industry. The second one is going to speak a bit about the supply chain constraints that are generally seen within EV industry across the board in the recent times. It's just that you can only mass produce with the material that you have. So it's an essential block in the whole building for whenever we talk about mass production and challenges. And the third one and the concluding section would be for the manufacturing and the testing techniques that over the time the industry has either been struggling with or had a very unique requirements, which is challenging for a ramp phase itself. So starting with the first one, as Samad sir already mentioned, I've been working with Tesla since May 2017, sorry. And initially I started as an intern working across a different organization. for them across General Assembly for Model SMX and service team, and then had an opportunity to start working with them as a quality engineer on the high voltage batteries for Model 3 and Y, and recently moved as a new senior quality engineer for all the new program and the factory launches um, for everything that Tesla has to deal with in terms of HV battery. So that's that. And not wasting much of a time on that. Diving into the first one for today is just like what has been the market trend over the last decade with the EV itself. EV still only accounts for probably 4 to 5% of the global new passenger vehicles of 2020. For 2021, it hasn't fully concluded, but based on what the data is available as of now, it seems to be growing by 2 to 3% on the annual sale, with 7% of forecast overall, uh, with year-to-year growth of 67% that was observed in 2020. If the same anticipation is being believed for 2021, then it would be in the same 65 to 70% of year-to-year growth of what the penetration of the EV would be for the new vehicles being sold. This is a tremendous achievement for the industry in general to, in such a short time, to achieve such a big high percentage penetration overall with the whole thing. With China, European Union, UK, and US account for overall 90% plus of all the global EV sales that happened for the year of 2020 and also for the earlier years as well. Lately, they have been the leading nations to set up the trend for the global communities to basically hit the ground up and running when they are ready for and prepared for it for their based on their own infrastructure and needs. Um, on the graph on the right side, you can see that what kind of a trend has been observed with an EV industry, which probably very few and never before with an automobile has been seen. It's just that 2008 was the first year where officially first passenger mass-produced EV vehicle was launched. Yes, there have been vehicles before that that have been either electric, but they were limited production or were a prototype or a concept vehicles. But nothing was with an intention of customer saleable mass produce. In 2008, Tesla Roadster was the first one to come out. And since then, you can see that within a span of just under 1.5 decade itself, the industry has gone from a, a luxury vehicle that very few could understand and adopt to a mass adoption across the whole globe. Within just 5 years from the first vehicle launch, the lithium-ion battery cost was pretty much under 50% from the first one. 2014 was the year when not only the automobile private sector, but also the third party also started introducing the charging infrastructure, which was adopted across the different models. And that was the year that is considered to be a turning point where the charging infrastructure across the globe started to appear at a different pace. 2015, the famous Paris Agreement was being signed by all the leading global nations, where its significance for the EV industry was that for that targets to be achieved for the carbon neutral and the pollution curve, that as a whole community that we are trying to do cannot be achieved without the automobile industry itself also contributing there a bit more, and EV seems to be the route that helping that cause until some new more technologies unblock itself over the course of time. And so forth from there onwards, the curve has been exponentially steep, which is a good thing. Since the start of COVID era, that is probably from Feb 2020 until end of probably this year itself, the growth or the in general EV new innovations that came out was much slower than what was earlier happening or was expected to happen during time period. The main reason for it is that there was a sudden change in the consumer behavior that led to the all the industry leaders as well to cap the spending that they were doing on the research and development for their own product lineup with respect to the electric vehicles. That being said, nothing can be taken away from the trend itself. There are still some very strong motivation for the electrification of the whole industry itself. The environmental concerns that everyone agrees on, the constant instability and volatile gasoline prices, and the supply chain of it, which COVID era very evidently proved how unrobust that whole system is. The more and more tighter global political policies are coming up, which is also helping the EV trend to just keep rising in the direction that it needs to be. The consumers are much more open to the idea of electric vehicles than that they were previously. And with each and every passing quarter or even a month, that appreciation and the adoption of the EV is just going positively high rather than the other direction, which was not the case back in the day. And everyone now, for the majority of the part, agrees that unitedly everyone needs to come together, do some drastic changes for the sustainable future. Um, so that's what our last decade looked like, which set the tone for a century to come in terms of electric vehicles and automobile revolution. Um, Going more into what is expected as a growth for the EV market over the coming years, probably towards like end of this decade of 2030. Um, there is no doubt about the market growth and the development that will keep on happening in respect to reduction of the cost of the EV batteries and in general improving the quality and the reliability of those things. Um, as of now, the cost of ownership of the EV vehicle is already at par, if not cheaper, than the traditionally internal combustion engine vehicles. The idea is that by 2030, if we truly have to do the penetration through all the kind of consumer, uh, the cost of the EV battery has to be comparable, not just the running cost or the operating cost of the product itself. So that target seems to be that at the current rate would be 2030. Wouldn't surprise me personally if that happens even before 2030, but based on a lot of other external dynamics that plays a role over here for that to happen. Um, as of now, it seems to be that by 2027, we would see a light duty vehicles, close to around 40 million units of them to be running up and there on the road, which is with an assumed modest growth rate of 65%. And our current growth rate has been higher than that. So again, that's the target, which is would be a great milestone to achieve. But based on what the fundamental of driving this whole EV market is the climate and environmental concerns. As per the Paris Agreement that was done, the projects that were signed off and the agreement that happened was to have an alignment and a pathway to maintain the temperature rise at 1.5 degrees centigrade. And for that to happen, the definition of electric, including the battery electric and the fuel cell, needs to be close to 75 to 95% of the global new passenger sales by 2030. And by 2035, it needs to be 100%. So though the industry is growing at a tremendous rate, there is a significant gap on what needs to be done versus what is expected to be done as of current. But as industry adopts the post-COVID era with the new dynamics in the supply chain, with the new dynamics of the consumer behavior and how the financial logistics in general operates, it's expected that 2022 onwards, the industry would be not just recovering, but would be hitting the ground much harder than what it was previously being done. And as you can see on the graph on the left side below, the IC engines are also expected to grow over the next couple of years, but probably mid this decade, it would plateau out to start reducing in number of new sales that happens on that front, and the penetration of EV vehicles in general, either the fuel cell or full high voltage lithium ion based batteries would be increasing over the span of this decade. So definitely interesting time ahead for us. Um, Leading into the second topic and one of the main, technical talking point for today is the major supply chain constraints. The reason I wanted to add this to today's slide, and in general, anyone ever ask me for challenges in mass production, I try to mention the major supply chain things is you can only produce from the material that are available to you. And the quality of your production or your manufacturing is directly dependent on the quality of your tier one and tier two suppliers, and probably going all the way down to the sand and metal raw itself. But it's essential given that how quickly this industry has been growing. Not a lot of adoption or the time had been given for the suppliers to innovate at the same speed to understand the demand of how it needs to be done, what needs to be done, which is very unique to the EV industry. So it's super critical to understand this aspect as well. Um, the three main constraints that has been seen so far has been with the cell manufacturing raw material itself, with the lithium-ion cells availability to make the HV batteries for the electric vehicles. And the third one is the PCBAs and FPCA components, that is the printed circuit boards, the solid semiconductor chips that are more commonly known, and the flexible strips they are. I'm pretty sure that most of you on this call would have heard some kind of news on the shortages of the semiconductors that have hit probably every industry, consumer industry that can be hit, where it's being used. So starting with the first major one, the PCBAs and FPCAs, um, they play a very fundamental role for the battery management system technology itself. Uh, they are not just used in that, but that's probably the most safety critical function of that in the EV vehicles. Um, Beyond that, the consumer demand for the electric vehicles is such that today that it is generally expected to have a lot more features and goodies in it, which with every new addition features that you try to add, it would require some capacity of new PCBAs or FPCAs to be introduced, which are already scarce in their quantity. They don't come easy. They're difficult to be designed for the EV vehicles. And even for the design that we understand, it's not fully well-defined designs. So going a bit into the fundamental role for the PCBAs for the battery management, it's supposed to help with the voltage, measuring the total voltage or the voltages of the individual cells, temperature in terms of average temperature or the temperature of individual cells. Again, those are safety critical functions because if your temperature of the cells are rising, which is a common thing to happen with the EVs, you want to shut down the vehicle in a safe manner. You don't want to keep it under operation, or you don't want it to keep under charging or discharge, whatever is causing that overheating or rise of temperature that is not predicted. So again, all of those things are controlled through PCBA. So super critical and super important in that manner. It also helps with the state of charge and state of health measurements across the battery through the operations, through the charging and discharge itself. And unlike the consumer products where this is being used in our laptops, in our phones, now our watches, and pretty much everywhere that we see, it's a common thing. It's not a new industry that is coming up. But what is challenging about it is first is the design aspect of the requirements for the EV vehicles. For every volume requirement, for every square inch requirement from the surface area perspective, it is very scarce in terms when it comes to EV vehicles. Like you might be thinking, oh, why can't we just fit one chip here and there? No, like you would be surprised that the clearance that the whole product has been packaged together is even fighting for like 10 square inch here and there. Or sometimes we are also dealing with like a couple of millimeters of clearance itself. So that's how densely this whole product has been packaged today. So there's already a limited space available within the battery pack itself that adds a challenge for the physical design of these systems. The circuitry needs to conform to the volume of space available within the battery pack package without obviously compromising the mechanical or the operation of the battery pack or the function of what it's designed for. It also has to be not so tightly packaged. There is a fine balance on the lower side as well, that it starts violating the critical creepage clearance that it needs to have based on the voltage and the amperage that you are trying to power it through. So those are the constraints on the volume and surface side, leading into the mechanical shocks and the temperature conditions. They must continue to operate reliably and accurately while withstanding the harsh conditions. It could be including mechanical shocks and vibrations, such that someone might be driving those cars on the potholes based on the road conditions that it is. We have also seen some of the people driving the cars as an off-roader, this car that is designed mainly for on the regular roads. They have been driven on rocky mountains, things like that. A few people have also drove it through the fully um, flooded tunnels and even water bodies as well. So it needs to take all those environmental exposures and withstand them. Obviously, the vibrations that the vehicle goes through the life of its through its life, it's much more higher than much of the consumer other products that uses the same component. The standard electronic devices are generally used in environments of less than 75 degrees centigrade, but for automotive, the range is much more aggressive considering the factor of safety that one has to consider. So the same vehicle that has been manufactured can go to someone staying in a Sahara Desert or someone staying in as cold as in Alaska. The same chip has to function in those wide conditions. So definitely the temperature range also has to be like super adaptive in nature. Precision of operation needs to be much more accurate, because for the other consumer products where this component has been used, it's more like it would be a dissatisfaction to a customer versus a slight impact to customer life when a failure occurs. But this failure over here, if it's not precise or it fails to function altogether itself, it could be a lethal in terms of safety as well. Non-functioning of this have led for some of the products out there causing a safety endangered risk, like hard shots or even a small fire. So again, it's super critical. And the last thing that adds the challenges to the whole thing is the intersystem compatibility, which essentially is in a way, there are so many mechanical devices that have been operating different systems of safety, active and passive. They each one have been designed by different suppliers, different OEMs. They all have their own coding languages, analogs and digital signals, which all have to be understood and adopted by this PCBA. So they have to be like super versatile in their nature and in their design. So these are some of the challenges that goes into designing the PCBAs, which also impacts at what rate this can be produced at, because they are not something like we decide to make something like this, and tomorrow that would be a tool that can fabricate this chips right and left. No, it's a growing curve. The industry is the PCB industry is also learning with the EV industry hand to hand, because they are learning in parallel and they're not leading the pack. They tend to become the bottleneck because the industry adopts to what they have and they have to consume, and consumption is the easier part than to manufacture them. Um, that leads us into the supply chain constraint beyond just designing is the demand or the requirement of the PCBAs have exponentially grown so high, but the production growth rate has remained steady for the PCBA boards. Um, it's not just because the industry doesn't want to grow with it. It's a lot of capex investment that has not been lately happening with, just because there is still an uncertainty around what kind of a PCBAs would be required, to what extent their consumption would be. Is it artificial growth or is it a permanent growth? And those uncertainties around the demand ramp has constrain the PCBA industry itself to focus a lot on the automotive side. It also needs to be pointed out that at this point, the same PCBA chips that goes into our performance laptops or in some of the high-end tablets are the same configuration chips that are also being used in an electric vehicles and in HV batteries to an extent. That means that a lot more industries with a deeper pockets are competing for the same product into the market with a scarce availability that it is out there, which is also making the whole supply chain constraint much worse than what it should be. Um, as more and more COVID has made the industry realized is the global political uncertainty and dependence on a certain region versus the other ones um, when happens and what the political tie up with the country governments across each is very important because a lockdown or if there is an air shipment that is not happening anymore because of some of the policies, it severely impacts. So those are also now that the industry is learning and adopting those dynamic nature that was exposed because of the COVID is now getting um, addressed and which will take a time of some couple of few more months. It is based on the post-mortem analysis that was being done on this whole constraint side, based on the IPC survey that came out in Feb 2020, which was considered to be one of the peak for the COVID times, the electronic industries was already struggling with having this component by certain degree. It's just that COVID made it very worst and difficult to recover from. But this time was about to come, regardless of whether COVID happened or not. It's just that COVID made it happen sooner rather than pushing it back few more years where this same scenario might have coexisted. So that's also an important thing to understand is why the production growth rate has to go up. Despite everything, the automotive industry is expected to continue grow through 2022 at 28 to 32% in terms of the demand requirement for these components. But the industry itself is expected to grow by 11 to 13%. This gap is supposed to be bridged by optimizing the current PCBA boards by making them function a lot more things than what they are right now, thus reducing the drive for the number of quantity that goes per vehicle. The recent shortages have definitely not only delayed the introduction of the new vehicles into the market, but has also forced the giants like General Motors, the Volkswagen, the Audi, Nissan, even Ford joins the list recently. They all had to cut down the production volume due to the part shortage, and there have been days where they had to shut down the production completely because of this. So it's a very critical component, which is going to be interesting how industry evolves and comes over the whole design challenges and supply chain constraints. Because of this sudden rise, the second thing that went into the constraint category was the lithium cells itself. Again, lithium cells is not new to the industry itself. They have been first commercialized and have been being out there in the market since 1990 for the ones that are being used in the EV vehicles right now. It's just that the demand over the last decade for the portable electronics market, plus the EV market itself into the picture, has completely changed the scenario. Everything today is mobile. Everyone wants things to be portable, right from their laptops to their mobile to their keyboards. Even televisions are now becoming portable to an extent, and everything is going to be driven by a battery. And lithium ion is the one that is leading the pack as of now in terms of supporting this demand drive. And it's not because like there aren't other technologies that can do the things. It's just that lithium ion single-handedly, if you take the advantages that it has to offer, versus even if you account for the drawbacks that it goes with, it still outweighs the next closest battery technology that we have that is considered to be the lead acid and nickel zinc one. They are the other most matured battery manufacturing technologies that can do the job. But the problem with the lead acid is that though it can be produced in volume and it's comparatively lower in cost and has a super matured life, it cannot be discharged more than 20% of its capacity. It has a very limited cycle time in terms of like how many times it can be charged and discharged. Its energy to mass and density is tremendously questionable, and it requires a time-to-time maintenance, to the point that even 12-volt lead acid batteries are getting replaced, if not already replaced, to some other kind of battery technology that we have. So definitely it was not a first promising option when we are talking about a high voltage battery that has to function through a life cycle of probably 50 to 100,000 times through its life cycle, if not more. And then also needs to be super light in nature and easy to manufacture. The nickel zinc, the problem was that, and it so far still makes it the biggest drawback of not exploring the technology any further, is the tendency for it to have the dendrites on it when it's going through the course of its life. Dendrites, it's nothing, it forms like a deposition of a conductible path because of the environmental exposure, such that it will bridge the positive and negative within the battery itself that is closest to each other and create the short. And those shorts can be, again, very dangerous because they are not very small, minor shorts. They are hard shorts that are being caused. And just due to that, lithium ion, it has the required energy density, it has the performance requirements, not just in terms of like capacity and store the energy, but also a super wide temperature, easy to manufacture, and has the reliability and maturity that can help lead the technology for now. That being said, obviously there are other uh, research that are happening to explore other battery technologies can replace the lithium ion, but only time to say when and what it would be. Solid state battery technology is certainly one of them that is very much creating the noise, positive noise in the market to be potentially the next replacement for the battery technology. Um, some of the challenges with the design of the lithium ion is also similar to what we talked about for the PCBAs and FPCAs in the previous section. Um, they are not fundamentally, though they are the same ones that are being used in our day-to-day AA or AAA battery cells, they are not essentially the same beyond just having the same working principle and the uh, physical dimensions of it. Again, it needs to have super optimized volume and the surface area, because given the shape, the cylindrical shape of this, if they are big and their energy density is not as much, then you would have a lot of voids that are not being used, and you are carrying unnecessary weight, which requires energy to be carried around. So you want your battery pack to be as light as possible so you can optimize the other systems of the vehicle. And the majority of the weight, if like close to 90 to 95% of the weight of the battery comes from the individual lithium ion cells that are used inside them. So it's very critical for them to be as optimized as possible. They obviously go through much more mechanical shocks because all the local frequency that travels from the road to the rubber to the tires, wheel, suspension, those are the frequencies, even they want to be isolated from the battery pack, they go to the lithium ion cells terminal or to that bottom. The reason for it is that based on the current vehicle architecture that is in the market right now across all the competition that is there, they all are using the HV battery as a safety mechanism, as a part of their own vehicle primary structure. It's not an add-on to the vehicle. It is a primary structure. That means it is meant to absorb a lot of dampening, vibrations, and those things into it when a collision happens. That means that even day to day, when the car has been driven around, those frequencies make their way to the lithium ion cell core itself. Temperature conditions, again, lithium ion, not all the chemistries of the lithium ion can sustain the wide temperature, but the one that are widely used, they can currently take, and they should be taking at least minus 40 degrees centigrade to all the way 60 degrees centigrade. And that is with an assumption that your battery management system is working as intended in a park state as well. though they have been tested for much higher temperatures. There have been conditions where it has been tested all the way to even as high as 95 degrees centigrade. There is no known driving factor as of now to test any of those technologies beyond -4 degrees centigrade on the lower side. So that number has always stayed segment for quite a few years now, but the upper bound just keeps on varying as the global temperature and the operating temperature of this vehicle has been changing and have been increasing. The last is the fail-safe systems. Again, this sometimes have been overlooked by many of the competitors as well. The reason for it is one needs to understand is that all the testing and understanding has been done when the vehicle has been developed on like how the cells function. But a less study was initially done on how would a cell die at the end of its life when it's supposed to die. It's very important for the batteries in general that for that to be fully understood because there are two kind of a dying nature of the battery cells based on the design and the chemistry itself. Is one is a subtle way where it starts impacting the range or the performance of the HV battery, but does not create a negative impact otherwise to the product. That's a subtle way of saying the battery died. The more aggressive way is when towards the end of the life itself, the cell becomes so unstable, the chemistry becomes so unstable that in some of the scenarios, it can even burst itself into flame. That is something that we never expect or we don't want in an EV, especially when someone is driving around. So those are also some of the driving factors in the lithium ion cells. The other one is when there is a short or sudden rise of temperature or voltage that have not been predicted, the venting, how does the venting happens in the cell? Ideally, you want the cap of the cell to be opened up from the top such that it releases the pressure away from the operation of the vehicle and the passengers that might be sitting inside the cab and release all those pressure towards the road or the side of the vehicle. So those are also the systems that has to be designed in the cell itself so that when those scenarios are being came across, they are being dealt in a way that it's designed to be. Going towards the supply chain constraints, given that, okay, we understand it's difficult to design, but again, the same narration, it's difficult to manufacture because the design has still been evolved. Every year, there is a new design of lithium ion that is going out, which is not nearly same what the current or the previous generation was, to the point that they cannot be interchangeably used. So the industry is adopting to those dynamic changes, and they are also skeptical in a way to what they want to adopt. And do they want to adopt every iteration that comes out, or they want to skip one iteration or go to the next? So depending upon how those dynamics are being played out, the supply chain is being strained because of that. The total demand for the lithium-ion batteries was over 200 gigawatt hour in 2019 alone. The forecast demand for the electric vehicles, without accounting for any other thing, based on the current capacity of what is being produced, uh, we are looking at close to like 350 gigawatt hour by in next couple of years. Just for the perspective for this group, 1 gigawatt hour is equal to 3.125 million photovoltaic panels or 412 utility scale wind turbines, or it's equivalent to 110 million LEDs. So it's a tremendous amount of energy capacity that we are talking about over here, which is only and only required just for the electric vehicles without considering the capacity increase of the vehicles, the demand increase in the vehicles, and all the other factors that is just going to make this number much, much higher in reality if all the pieces in the puzzle fits perfectly well. Um, as of February 20, the Audi again had to like temporarily stop its e-tron production for a while because of the battery supply constraints that they were going with. They reduced their production target as well, not just for 2020, but also for 21. It was the same narration where the companies like NIO, Xpeng, the Jaguar, E-Pace, and all the other major uh, EV manufacturers that are out there, their target has been reduced, even though they know how to manufacture the EV vehicles right now because of what lithium ion cells they can get their hands off today on that. Um, there are some of the largest manufacturers like LG, Panasonic, Samsung, CATL, BYD. They all are like very well known and the biggest in the industry of their own in there. Even they combined together do not have the capacity to meet the demand of electric vehicles of 2020 as of that end. And 2021 has not ended yet, but that has been the same narration for 2021 as well. The companies have been consistently outpacing the manufacturing capacity they have uh, more than what the cells, lithium-ion cells can be produced at. Um, Again, for the cell production to take place, the necessary supply of the raw materials needs to be there, such as lithium and cobalt needs to be available. That gives us a nice segue to go into the last constraint point of the supply chain, that is lithium ion cells in its own is a technology that has been evolving over the time for manufacturing, but the availability of its raw material components is also a challenge in its own because of the form that it is being sourced in and also what is readily available, and we are equipped for that so resources to be distributed across the globe. So in the batteries, as most of you already know, lithium ions move from the negative electrode through the electrolyte to the positive electrode during the discharge, and when the and back and forth vice versa for the charging phase of that. Um, the lithium ion batteries generally use the lithium compound at the positive electrode and then graphite based compounds at the negative one. Just like any other products out there, the quality and the reliability performance of the battery cells and of your HV battery is directly proportional to the quality of those raw materials. And you would be surprised for knowing the number of quality grades of materials that you can find out there, ranging from all the kind of costing. You don't want, ideally you want, but sometimes it's like getting an perfect condition of this material is considered to be an over engineering as well. But you don't want to like have too many of um, unpurified material into it such that it starts impacting the performance. So there's always a constant battle of finding that right mix and resources that you want for your lithium ion. Some of the major raw materials are like lithium. It's usually used in all the EV batteries that are currently in production. Lithium is found on the EV's anode side or negatively charged post. The nickel, the next one, makes up anywhere from 33 to 80% of an EV battery's cathode based on what chemistry and the compound it's being used. Um, Nickel has a higher energy density, so it aids in extending the range capacity of your HV battery. Cobalt combines with the nickel to make up for the cathode in many battery technologies and chemistry in its own. So lately, the adoption of cobalt has been increasing by quite a margin. Manganese can be used in batteries instead of cobalt as a substitution. Manganese could be one of the tickets for us that can lower the EV battery cost into the future. But there are some nicks and challenges that comes uniquely with the use of manganese instead of cobalt into the HV batteries. But given the cost and economic attraction towards the material and the availability of it, it is very highly explored as of now. And probably in a year or two, wouldn't be a surprise if some of the products start hitting the roads and suddenly the EV trend starts going towards that direction. The last one is graphite. It's the second most commonly used component in the batteries in terms of volume and weight or mass. It's used to make the anode in the batteries. Graphite allows full power to be used until the battery is discharged. because it has a flat voltage profile nature of itself, which is comes very handy um, in its own. Um, the ongoing trend of the battery capacity is projected to be continuing with hand in hand, obviously, with electric vehicles, because irrespective whether it's a fuel cell based or it's a fully electric high voltage battery based, both of them requires an electric battery in it, irrespective of the nature. So that's where it's important, and it will always keep on growing hand in hand with the industry itself. The global electric vehicle battery capacity increases from around 200 gigawatt hour per year today to 1.5 per year in 2030. That terawatt hour capacity, it's tremendously high, and you can see that if it is to be assumed that we cannot further optimize the performance or the energy density based on the same chemistry compounds that are being used today, then it is estimated that the material demand for the batteries of the electric vehicles for 2019, for example, if it was 19 kiloton for cobalt, then for the same one in 2030, the cobalt demand would be 180 kiloton per year. That is close to 20x growth that is supposed to be happening to meet the demand over the span of next 7 to 8 years. Same is the story with the lithium, where in 2019 for the demand it was 17 kiloton, but it's expected to meet by going upwards to 185 kiloton. And for manganese and nickel from 22 and 65 kiloton respectively to all the way 177 kiloton per year to nickel 9 to 5 kiloton per year. Now, nickel again have different classes. So class one nickel has been used mainly in the lithium ion batteries. So as you can see, not enough growth in the output due that is there, and which is constrained by not can we find this material. A lot of these materials are like available in abundance and abundance and abundance, but the constraint is whenever the mining takes place, it has a negative impact on the environment around it. Uh, they, the way that they are being filtered, the way that they are creating the waste in terms of the supply chain from like putting it into the big containers, moving them to the plants, to the where the manufacturing of cells occur, that is very high, which is concerning enough, which limits by a lot of leading nations of what you can mine, when you can mine, and how much you can mine. So because of that, even the material is available, it is governed by those things, and that is directly impacting the quality and the volume that is available to build those lithium ion batteries, and then at what rate we can build. So these are the top three constraints from the supply chain side, based on my perspective, obviously subject to some of the other interpretation that the industry is going through, which directly impacts to what we can mass produce and when we can improve or increase our capacity. Going into the last segue for this one is the manufacturing techniques of the HV battery itself. The general automotive battery packs that you would see in today's industry is manufactured in a way of like a battery pack to a module to a cell structure. It is that order that it goes into from parent to the child. The actual designs might differ slightly based on what the battery architecture is, which is driven by the capacity and the power you want to have. Uh, One may connect fewer larger battery cells with a high individual cell capacity in series. For example, Nissan Leaf does that. They can be clustered into the modules, or alternatively, the multiple small battery cells with low individual cell capacity can be connected in parallel and connected to the modules with a high capacity. That's a general approach for the Tesla vehicles, if you see. So using Nissan and Tesla as an example over here. Some of the manufacturing challenges that comes with this EV is it's a new processes that needs to be developed. The industry is still very young, where we have been making the traditional IC engines for over a century now, but this industry has only been starting to make the mass production of the HV batteries for last 13 to 15 years only. So the processes are not super optimized. They are not super understood on what the needs are, what the requirements are, and with the constant evolving and the change of the physical nature of the design, makes the manufacturing process development even more challenging than what it is. Um, the design and the fixtures itself, there is no readily available design and the fixture or the equipments, which again you could find for the EV industries, um, for the traditional IC engines itself. But for EV, there is no readily available third party or OEM that can support that. The safety precautions of this is also tremendously high. The reason for it is that from the day one itself, the moment it comes in, the battery cells, they are live. They have the energy, where it's electrically charged to some capacity because you cannot have a zero state of charge battery cells come in. It will just create a lot more waste and it kills the optimization of the manufacturing process. They have some kind of energy. So the safety precaution that is needed is also very high and challenging in its own way. Uh, Beyond just electrical charge, the discharge, electrostatic discharge, that is ESD, is also very critical in the manufacturing of this HV battery. So in a way that where the touch points are, how it is touched, how the grounding is being done between all of those things, the safety precaution is also very critical in its nature. Um, and then the final is the disposition of the non-conformance material itself. Obviously, not everything that we manufacture is a customer sellable. For every industry, there is a certain level of waste that is being created, including this one. So those are some of the manufacturing challenges that we come across. The critical processes, as a general manufacturing or the, the, the workflow of this would be is that from cells, a cell array assembly process occur. Then an interconnect process would be happening on those cells that are within the cell array. Then you look into the inspection and the packaging and the handling of the product based on what your physical battery architecture is. The final is testing of the product, and then the product is being shipped out. So that's a general workflow and the critical processes of it. So going into the first one, the cell array assembly process. This is one of the most critical aspect of the manufacturing, and I would say probably the most challenging one across all the four. The reason for it is that based on what your battery architecture is and how that needs to happen, the individual cells needs to be brought together, but they cannot be far too apart because then it increases the volume far too much and the waste occurs. As you can see on the image on the left side, if the cells are just put into a rectangle shape, then the voids that it creates is far too much. There are unutilized voids. But against, if you use a honeycomb kind of a structure, which is showed on the image on the right, the cells can be optimized, but that means that the placement of the cell has to be far more accurately and has to be repeatedly be perfected every single time that you do. These cells cannot be manually handled. They have to be automatic in nature. Um, and that means that when you are designing the manufacturing equipments that needs to handle these tiny cells, need to repeat the operation again and again, um, it's not just the speed or the precision, it's also at what impact those are being placed. All those things play into the constraints and the requirement of the manufacturing process itself. Um, Against the cells needs to be also carefully handled during the manufacturing due to the risk of the thermal event itself. Because if you crush a cell or electrolyte leaks, it can basically go into thermal runaway, causing a fire. Um, the second process that occurs in general is the interconnect process. Interconnect process is nothing but it's connection of all the individual battery cells to basically connect to the plate or the other substrate material to complete the circuit and start utilizing every individual cell to make just into a bigger battery pack or capacity that is there. Um, it creates both mechanical and electrical stability of the battery. The adoption of different joining technologies influences the characteristics and also the battery architecture to define the performance capacity and the lifetime of it. Uh, the driving factors is the electrical and thermal requirements, the material requirements, mechanical requirements, and economic requirements. Again, it's a topic of its own to deep dive how each of those impact the interconnect process there. But in nutshell, it's what's needed is that they need to last the life of the product. They need to be able to draw such high voltage and amperage in a safe manner. But at the same time, when an abnormality occurs, they need to fuse such that they isolate that particular cell or the battery completely, thus safeguarding the product and the customers that are driving the vehicles around. The generally known methods for the interconnect are ultrasonic welding, wire bonding, soldering, brazing, laser beam welding, resistance welding, and friction stir welding. Many of this is still very new in terms of manufacturing technologies, at least for the use case of HV battery. The three leading ones are the ultrasonic, the wire bonding, and the laser beam welding itself. Um, of these three as well, the wire bonding is the leading one that is being currently used. The reason for it is it works on the same principle as what the ultrasonic welding does, but it bonds one end of the wire on the cell surface, then it creates and induces a wire, a thin wire, and then applies the same ultrasonic welding on the other end where to the plate or the current collector, the name of the plate that generally is known with, it needs to be welded to. This allows more manufacturing variability of the cell height, the cell placement, the surface of the cell, the surface of the plate where it's to be bonded, and it can be automated and it's easy to test them. So those are the reasons in general why the wire bonding is much more widely used than the other industries. But laser beam is the next in line that is rising very rapidly through the ranks. And in coming years, if I would have to bet on the technology, it would be that one because, again, it's a non-contactless, completely high speed, very good precision, easy to test, better reliability, and the best of all, it can create a pattern of the weld that is much more optimized than any other weld technologies that we have out there for the HV batteries. In terms of inspection and the handling of the product, industry is not matured enough to have a readily available inspection methods that we need as of today. Even today, every time we come up with a new product, the inspection that we have to do, we work with leading companies like Cognex and Keyence cameras and other automation companies to build the inspection tools and the softwares and things like that for us to be able to inspect the product that we are inspecting for. That's one aspect of the challenge. The other aspect of the challenge is for internal combustion engines that have been manufactured over a century, we know exactly what needs to be inspected, what can go wrong when a certain parameter is failing by what degree. Over here, the technology has not matured enough for us to understand every nicks and kicks of the whole design. So a lot of the things that we are trying to even inspect for, we don't know if we should be inspecting or not. That adds a new complexity to the whole game over here. The third is also the accuracy of what the inspection needs to occur at. There are some of the inspection that has to be as accurate as plus or minus 10 micron on a cell surface that is like 70 millimeters in length or 21 millimeters in diameters and things like that. It needs to look like tens of thousands of products per second and make a decision on such a scan to say whether it's acceptable or not. Just because a dent on the cell, hypothetically speaking, can also create a safety critical failure because a dent will push the electrodes and the jelly roll inside it against each other. And during the life of the cycle, it expands and contradicts such that it swells and leading into an internal short of itself. So again, super critical inspection, very difficult to do, and very less products, not even companies out there that can do such an inspection. Um, This is just a tabular form in terms of to show how a different battery architectures can exist in coexistence with each other. For example, you can see that Nissan Leaf has 58 modules in it, versus Tesla Model 3 and Model Y only have 4 modules in it. Now, number of cells and number of modules in a battery pack does not correlate directly to the capacity of the battery itself. It just intends to say what kind of a battery architecture the company or the designers have intended to go with. Everything boils down to the energy density per cell and how it is being utilized, and things like that. So if things are connected in series, then it will give you the power. If they are connected in parallel, it will give you the range and those kind of things that you want of your battery pack. So there is a trade between what you want to connect in series and what you want to connect in parallel. Uh, there are three main critical testing that happens for the HV battery. That is testing for isolation, testing for continuity, and the functional testing for the PCB boards and HV joints. The test for isolation is essentially making sure that all the electrical connections that you are making is grounded correctly. At the same time, they are not bridging across the bricks or the circuit in a way that is not designed for, or it can lead into a hard uh, short, or if the current is leaking continuously, then it can act as a resistance, which again reduces the performance of the HV battery. So the hypot testing or IR testing is the method of doing the um, test for isolation. They both work on the Ohm's law, where you apply a known voltage, you measure the current, and you want to have as high of a resistance as possible. If it's below a certain threshold, then it would fail. So in HiPot, you basically apply the voltage through the testing time period, and anytime it violates the limits that you have set, it fails. Wherein for insulation resistance, you keep on applying the voltage, you allow it to stabilize, and then at the very end, you start measuring the current, and the last instance of your resistance value is what it is recorded to make or pass and fail. So depending upon what your device under testing is and things like that, um, you decide whether you want to do an hypot testing or you want to do an IR testing. There are, in general, two kind of testing that happens with respect to isolation. One is the qualification testing, and the other is manufacturing testing. Qualification testing is more like a design testing to make sure that whatever the isolation barriers that you have done is able to sustain the voltage that the product would be expected and much beyond during the product life cycle. Versus the manufacturing testing is to make sure that we ourselves have not induced any failure into the product such that the isolation has been violated. So that's how the qualification testing and manufacturing testing has been varied. Hyper testing is much more widely used for the manufacturing testing across the industry. Um, Again, it needs to make sure that electrical components are isolated enough to prevent the sparks. If the sparks are momentarily, then also it should be able to detect. And then it also makes sure that during the operation, if someone is unintendedly touching something, they do not get themselves exposed to some kind of a shock or any of those deadly exposure that one has to go for. So again, super important isolation. Next to it is the test of continuity. Um, Again, we are making so many of connections. Thousands of cells are being connected. Thousands of PCBs are being used across the EV. We need to make sure that the product, before it leaves the factory, it is connected in a manner that it can deliver the quality and the reliability and the safe nature of its operation that it is expected and designed for. So there are different, that's where the test of continuity is being done. Again, the core principle is again the Ohm's law here, but it's directly opposite to what the test of isolation is for. Here, you want to see as less of a resistance as possible to understand the continuity is acceptable to its limit. There are, depending upon what size of the product it is, what kind of an accuracy you're trying to achieve, different equipments are available in the market um, that are readily available based on the semiconductor industry itself that you can use. There's a flying probe, a fixed bench testing, a frictionless in-circuit test, and software-based testers for like specific purpose. Software-based testing is something that is still upcoming and new. Not all the generations of uh, the chips can be able to be tested in that manner. If it's the more recent ones and how they have been utilized into the system, it can or cannot be tested. Flying probe is again, it's a bunch of small pointy needles that makes a physical connections to the touch points itself. And fixed bench testing is something that you have probes that are already mounted in some kind of a pneumatic Z traveler, which is a constant in Z axis traveler, and always comes down and makes a contact to the points that it needs to be tested. And then frictionless in circuit testing itself is also more or less a bit like what the software based testing is. So, talking a bit more of the flying probe testing, and I'll start the video of the flying probe at the bottom to give a prospect of it. But essentially, this pogo pins can makes a contact with the PCBAs every time it has to test for. The pins that are touching is called as in-circuit testers or ICT in general, and they can make like tens of thousands of test connections in parallel. So two of the pins are voltage, two other pins are of the current. So it's constantly measuring the source voltage and the detection voltage, the source current and the detected current, trying to measure the resistance in parallel and seeing whether the connections is good. Um, the video that is being played at the bottom, it's a super slow-mo video of how it's operating at. It takes like less than a millisecond for it to complete under hundreds of testing that needs to be done. So super nice technology. The frictionless in-circuit testing, it just generally, it's an adoption between, as I said, a software-based and something that is the flying probe one, but it is not as matured and has a lot of limitations on what it can be done. It can only operate in two axes as of now, but with a more complexity that is coming to the HV batteries and how the interconnect and the other connections are being made, the requirement of the whole thing has been gone to the point that either you want to do a software-based testing or you want a three-axis testers, which are only couple of them that are available into the market as of today. Um, as a last note, for this group and for this audience, I want to leave behind is some topics for the food for thought is the recycling of the EV batteries. It's not a constraint, it's not a challenge, it's not a lot of talked about thing as of today, but certainly we expect this to be a challenge that has to be addressed probably by end of this decade, if not sooner, because all the early battery life products, all the waste that has been accumulating for all the new startups and already existing mass manufacturers, they have to be tackled through. Uh, they are not something that we can just throw anywhere. Once a lithium-ion cell has been made, it's biohazard. So they need to be handled very carefully and disposed in a very mindful manner. Because at the one end, if we are driving the culture of environment by having the EV vehicles, we cannot create an environment concern by wrongly disposing these EV batteries. And also the ones that die, how we're going to recycle them. Redwood Materials is one of the leading industry out there that is upcoming with the recycling concept of the EV batteries. Um, the other thing is what would be the next iteration of EV battery cells? Yes, today everything is based on lithium ion cell. Is it going to go towards the solid state battery? Is it going to go to a completely new technology that has not been fully captured yet? There are some fusion based, nuclear fusion based technology as well that have been conceptually proven. Just the imagination is the limit as of now for what the next iteration of EV batteries is going to be. That would be replacing the established lithium ion. Is it a fuel cell versus battery cells? Always a debate that goes back and forth. Both have their pros and cons. As of now, industry has been much more biased towards the battery cells than the fuel cells, but only time will say what makes much more sense and what the mass adoption looks like in coming years. Charging stations, again, how does the consumer adopt with the charging infrastructure that we have currently, the direction that it's going to, what are going to be the charging times, is it going to get much more commercialized and entertainment based charging stations than what we have, or it's going to be much more traditional uh, fuel gas stations that we have that it's going to lead towards. So another interesting thing that is also driving the industry that is not talked much about and very few are leading as of now, but something that will pick up in a year or two, certainly. And the last one is the service centers. The operating requirement and the maintenance requirement for the EV vehicles is so low, and also adding that they are heavy software based. So remote diagnostic of these things allows to have a mobile service approach to this vehicle, which begs the question of like, what is going to be the service center um, in the few years or a decade or two to come with the electric vehicle taking a lead into the market? Are we going to have the service centers? Are there going to be so many numbers of service centers, or we are going to go a mobile service center with only a major repairs happening at the service center? Or there is going to be a new technology between now and then that every component can be swapped at your home place itself, where then the existence of the service center becomes more like a distribution center of storing the parts. So again, a lot has been happening, a lot has been talked about, but some of the topics that I just want to leave this group behind just to think about. And yeah, so that's all I have from my end for today. Thanks again for everyone for your time and opportunity. Now I'll open up the floor for anyone to ask any questions or anything that they would have for me.
Thank you, Jimit. Mm, any questions having from participant side may ask to the speaker. Yes, anyone have?
Hi, Jimit. Mahesh here.
Hey, sir.
Hi, how are you?
All good.
Uh, so I have one question. What about the second life of these batteries? Means whether we can use it again in low range electric vehicles or in some other applications like mobile phones and all. Is there any chance of using this?
Yeah. So technically, lithium can be reprocessed and can be energized um, if they are being done in a certain manner, such that it can be reutilized. Not necessarily it has to be under a cell phones. It has technical ability or theoretical ability to be reused into high performance electric vehicles as well. But how we recycle them is still a very big question mark as of now, because it cannot be of the same compound that it is currently being built with. Like your chemical compound has to change because current chemical compound, whatever energy or particles has to draw, it has done. So it has to be re-energized and used with a different compound. So theoretically, yes, it can be done, but it does not exist at mass manufacturing level.
And what about another material? Means lot of things have been talked about lithium ion and all. And since last many years, even mobile industry is also working on lithium ion, but they are not able to, let us say, provide sufficient output. So in term of range, let us say operating range up to more than 500 kilometers of range. Apart from lithium, what else things can be worked out in material sense? Means what other materials are there apart from this lithium ion? And all?
So there is another cobalt-based.
No, about regarding all these things, apart from this regular materials which are used.
Solid
There
state
is,
is also something that is up and coming. I'm not super familiar with that technology beyond what I have just read about the articles, but they are certainly have the, again, there have been a couple of companies that have proven the range upwards 500 and 600 kilometers, which can certainly substitute. The advantage of solid state is it's easy to manufacture and their life cycle is much wider and they might be cheaper to manufacture. But their reliability is still not proven yet, and that's what holding them back yet. But most certainly, lithium ion is not going to sustain for longer time. But what it replaces or gets replaced with, it's very much TBD. I'm not sure if there is another company called BYD and CATL.
Yeah.
They both are working on another concept of pouch technology, which is not based on lithium. They have done a tie-up with something called a mega capacitor side of the DIN. So usually mega capacitors are being used as an initial booster kind of a thing itself for a lot of heavy equipments and even in small of the EV vehicles. Their concept is to use the mega capacitors in a controlled manner, such that you keep on using it in small bursts and then replacing it with something HV battery. But again, time will say what
okay.
works out. So yeah.
Okay, thank you.
So any questions having the participant side? Otherwise, we proceed to conclude this session. So,
Hello.
happy to see you. Yes.
So I have one question, like, is there any chance to like better get damage and it cause like so much like risks? Like the battery can be busted as like eventually we see in like mobile phone like some mobile apps get burst and it cause like a lot of accident. Is there any chance of like electric vehicle too?
Yeah, it is. Because both how the mobile phone batteries are being manufactured is pretty much the same risk and the principles that goes into the electric vehicles as well. If we are taking an example of what happened with the Samsung phones back in the day, what happened was their pouch technology, the separators that were used between the anode and cathode was historically industry has been using 10 micron separators. They wanted to optimize it so much that they went to 8 micron separators without testing it to full life capacity, such that the separators gave up. And whenever the separators at that magnitude gives up early in life, there is so much of energy that cannot be controlled, which can lead to a hard short. And depending upon what and where the hard short happens at what state of charge, it can lead to a fire, which can be a mobile phone, your laptop, or even an electric vehicle.
Well, thank you, sir.
Okay. So we proceed to conclude this session. Happy to see you, Mr. Jimit, on this platform. As we know, a use of electric vehicle approach toward the society is positively moved forward, and you have nicely delivered the talk and give such a wonderful information about overview of challenges with mass production of EV battery pack. So on behalf of Automobile Engineering Department and Management University, I would like to thank you very much, Mr. Jimit. Whenever institute has need some inputs, we always invite you in further also. So thank you, Mr. Jimit, for joining with us and spend your valuable time for your busy schedule and accept our invitation as an expert speaker for this faculty development program. Thank you, Jimit.
Thank you so much, Agnesh sir. Always.